in the semiconductor industry for over 25 years. Prior to Achronix Semiconductor, where he is the CEO, he was the CEO of Achronix Semiconductor based in Montreal, Canada. Mr. Blake worked at Altera before Achronix in a variety of sales, marketing, and general management roles. As Vice President of Product Planning, he was responsible for defining Altera's programmable logic product solutions. Before Altera, he worked at LSI Logic and Fairchild, where he developed ASIC technology. He hosts Masters in Engineering, in Business and Microelectronics, and Bachelor of Science in Applied Physics and Electronics from the University of Durham in England. So ladies and gentlemen, help me to welcome Robert Blake.
Good afternoon, everybody. So I'm very excited to be here this afternoon and to get to participate in the 2018 CASPA Summit. I'd like to thank Danny Wah. I'd like to thank Brandon Wang and the rest of the organization at CASPA for giving Achronix the opportunity to participate and also help with the sponsorship for this event. As I've got to know a little bit more about the CASPA organization, I've been very impressed with the dedication of the extended organization. These are people that mainly volunteer their time. And what I've found is that as this organization grows, the proliferation of innovation and technology, the ability to help with communications, and the ability to help enable business innovation in many different geographies is really what this organization is all about. And when you look at the opportunity that we face in terms of machine learning, artificial intelligence going forward, it's these types of organizations that are going to help companies come together to bring the services and products that we need to be successful. I think many of you are familiar with this game. It's a very old game. I think it was invented about 3,000 years ago or so in China. And it's quite simple. You simply place white or black rocks onto the board, and as you place those stones onto the board, you try and encircle your opponent's stones. And obviously, it's a relatively simple game. But the piece that astounds me is that estimates have been made that if you look at the total number of legal board options on a 19 by 19 board, it turns out that that's 2 times 10 to the 170. I mean, this is a massive, huge number. And it turns out that may be as many atoms as there are in the universe. So on the face value of this, although it looks like it's a very simple game, in fact, it's very, very complex. Now, back in 2016, the AlphaGo team, which is a part of the Google organization, came up with some computer programs employing some deep learning techniques and deep neural networks. And they were able to beat an 18 times grandmaster at this game 4-1. I mean, it was astounding that that was able to be done. And I think that when you consider that, that's really a significant milestone in the development of artificial intelligence. Now, this particular application required a massive amount of compute resources and very, very complex algorithms. And so as we think about how we're going to transform some of these types of techniques to more general purpose applications that are going to affect our lives on a day-to-day basis, we're going to need some new things. We're going to need very, very different levels of compute efficiency. At the first level, what that means is we need to drive down the cost. We need more compute for less dollars. And the second piece is because these data centers are so large, we need to drive down the power consumption too in order to be able to make sure that this technology can go forward. Now, I think that there's three main areas in which these innovations are going to occur. The first of these is on the compute side, the second is on data transfer, and the third is on memory hierarchy. On the compute side, I think that when you look inside many of these artificial intelligence algorithms, you find that there's a lot of matrix multiplication, there's a lot of ALU computations. And so the first piece is enabling massive parallelism to make it easier and faster to compute these tasks. We've approached this from building a homogeneous type architecture because we like this approach because it enables us to have faster design, reuse, and portability. The second piece is in terms of data transfer. As you can imagine, in order to extract this data or extract this intelligence from this massive amounts of data that we're now collecting all over the world, you need to be able to transfer that information very efficiently. And so the next big focus is on data transfer. Highly optimized networks to transfer that data. Now, I think 10 gig to 25 gig move quite quickly. We're seeing 100 gig NAT right now, and 400 gig is going to be deployed very rapidly. And on the third piece of it, it's memory hierarchy. And when you look about memory hierarchy, what you really want to do is you'd like to be able to put the compute closer to the data. Okay? And so when you think about that, we have to look at the overall memory hierarchy in these systems to make sure that it's optimized from off-chip to on-die in order to make sure that these computational units that we're going to use are going to be working all the time. What you don't want is you don't want to build highly efficient compute and then find it stalled some of the time. So we need to focus on all of these three areas from a silicon standpoint at the same time. Now, we're at the very early ages of machine learning and artificial intelligence. And when you look on the left-hand side, what we see is the amount of research that's being done in algorithm development. Things are moving very, very quickly. And so as we think about silicon solutions that are going to solve these problems, we need to retain maximum amounts of flexibility in these architectures because things will change and they're going to change very rapidly. The second piece in the middle is looking at precision. And if you look at the work that's been done so far, and if you look at two main phases, either the first phase is where there's training, or the second phase is where there's inference. Traditionally, floating point architectures with high precision have been used in training, and more fixed point arithmetic has been used in the inference pieces. When you look at the chart in the middle, what you see is that there is a general trend in this marketplace to drive these algorithms to get very, very similar results and move down that precision in arithmetic from lower precision floating point and lower precision fixed point. And the reason that that's very important is this, is that directly relates to silicon area and it directly relates to power consumption. And so that's a very important piece. On the right-hand side, we talked about memory hierarchy and the importance of memory. Obviously, when you look at very large data sets that are going to be involved in these computational problems, you need to think very carefully about that overall hierarchy of memory. If you look at the chart on the right, you look at on-chip memories of very fast cache. You look at second-level cache, and you look at external DRAM. And you can see in those areas how fast the power consumption goes up in order to move data on and off chip. And so when we look at these things, we need to be able to consider all of these different areas in terms of optimizing silicon to meet these requirements. Now, when you look at the landscape of different silicon technologies that can solve these kind of problems, what you see is there's a continuum. I can start on the left-hand side, and I can look at CPUs having the greatest level of flexibility. And as I move to the right-hand side, you can see that we can move through different technologies that will get different levels of efficiency and then different levels of flexibility. On the left-hand side, clearly, CPU technology gives us maximum flexibility, but it doesn't always give us the highest levels of performance in these compute applications. You look at GPUs, and very clearly, GPU technology has become dominant in the training phases for learning algorithms. But one of the drawbacks is power consumption. These devices are very power hungry. When you take the next group, you look at ASIC technology on the far right-hand side. Now, clearly, ASIC technology always holds that promise of lowest cost and lowest power consumption. But again, the trade-off is in cost of the devices, but it's also a trade-off here in flexibility. Can you retain that flexibility as these algorithms and workloads continue to change? And then in the centerpiece of it is FPGA technology, and certainly we believe that that offers the right balance between retaining that flexibility, but also having maximum levels of performance. And what I think you're going to find is that all of these solutions are going to coexist together. In fact, some of the estimates from market analysis show that over the next 7 to 8 years, this market for chips in these different technologies is going to grow to more than $50 billion. And the FPGA-based portion of that could be as much as a quarter of that size. If you look at different end applications, and what we believe is there's going to be many different types of workloads. You're seeing from things of data compression and data security. You're seeing applications where we're doing facial recognition. We're doing video processing. There's genomic recognition or research, Monte Carlo analysis. And across all of these different application engineers that require very, very different computational acceleration, what you're finding is that on average, when you implement these functions in an FPGA versus a traditional CPU, you're typically getting 30x to 70x improvement in performance. That's not 30% faster, that's 30 times faster to 70 times faster. This is very, very clearly the kind of disruption that's needed in order to make this technology widely available and very, very low cost. Some of you may think of the FPGA business as being on FPGAs for prototyping only. But if I look back and I kind of give you the very quick history lesson of that, when FPGAs were invented in the early 80s, in phase 1 of this technology, they were very small and quite slow. And they were typically used for glue logic integration. You took a number of TTL devices on the board, you put those into a single device, you save power and cost. And the market didn't exist before, but it grew from 0 to $500 million per year. The second phase was much more exciting. It was in the mid-90s, and by that time, FPGA technology had evolved. And as that technology had evolved, it used the latest generations of semiconductor technology. The performance went up, power consumption and cost came down. And these chips had much greater capability. And it turns out, all of a sudden, they were starting to be used in a second phase, which was connectivity. And the reason for that was that there were companies like Huawei and Cisco Systems building high-performance networking and routing and switching equipment. They were finding ASPs from one vendor and ASPs or ASICs from another, and these devices wouldn't connect. And what they used the FPGA technology for was basically to solve that bridging and that connectivity problem and enable them to very rapidly roll out those products and services. But now we're entering into a very, very new phase. All of a sudden, this technology that you may have thought was a prototyping only vehicle, now that technology offers you massive parallelism for compute acceleration. And when I look at this side, we think that this market by 2025 could be a $20 billion market. And when you look at the applications, clearly it's in the data center. It's going to be both at cloud and edge compute. It's for sure in the networking space where we're trying to accelerate things in the network. It's for new things in terms of autonomous driving. It's for things like fusion sensing or sensor fusion. And then finally, in the 5G wireless infrastructure, you're seeing these technologies accelerate algorithms both in the radio base station and in the baseband functions. At Achronix, our focus is in 3 different areas. And the first of those on the left-hand side is that we build high-density, high-performance standalone FPGA data accelerators. We call those Speedster. Currently, those devices that we are in production on is 22-nanometer technology, and we're very rapidly moving to 7-nanometer technology that we'll announce next year. The 2 ones on the right are a unique value proposition for us, where in addition to building these high-density devices, what we've chosen to do is also offer our IP so that it can be integrated at a chip level on die, which is speed core, or it could be integrated in package by 2 chips inside a package or multiple chips in a package as speed chip. And all of those solutions for us are fully supported by a set of software tools that enables us to go from high-level algorithms all the way down into implementation that we call the ACE tool set. And what I would say about that is, in developing the company and the technologies that we've done, I'd say tool chain is probably one of the most important pieces of our business. Without a successful tool chain, we simply would not have a business. So if you look then as the end-to-end network, and you look at then where will these different technologies be deployed, at the top of this chart in the blue, you're looking at cloud and data center. The centerpiece of this, we're looking at the infrastructure market. And the bottom piece of this is in the edge. And when you look at some of the requirements in those, clearly, there's a massive need for increased computational efficiency. Clearly, memory bandwidth is very important to make sure that whatever these parallel processing units are doing, that they're going to be occupied all the time. You're looking for very high efficiency. We're seeing that security is becoming more and more important across all of these data sets. And as you start to look at the edge, you want to make sure that any of the devices that are going to be connected to the network, whether it's through the new 5G infrastructure or whether it's through the internet, you want to make sure that those devices are known devices so that they can securely attach and provide data flow to the rest of the architecture. In the centerpiece of it, we're seeing, again, deploying computation both from the cloud and into the infrastructure, and making sure that we can future-proof that. Again, we want to make sure that as things change, that as the computational workloads change, that there's sufficient flexibility in these architectures to adapt. Because you can't afford to redeploy these things. These are expensive opportunities. So when we transform that and we look at how our products play into that, first of all, for us, we're building high-density, high-performance data center acceleration standalone FPGAs, and those fit in the data center data infrastructure. And then for us, uniquely, with an embedded FPGA play, whether that is on die or in package, that enables us to be able to deploy deployments in infrastructure and edge, where obviously the requirements are for much lower density and much lower cost and power consumption. So if I sum up some of these things and I look at the trends, I think on the left-hand side, first of all, well, first one is massive need for more computational efficiency. We want to move the compute closer to the data. The second one, memory bandwidth for these things is as important as the compute resource. You can't have these engines stall and not be working all the time. That's part of the efficiency. The data rate requirements, we're seeing that Ethernet connectivity is moving up very, very quickly. It's obviously ubiquitous in its deployment, and that's critical. And so we see things moving from the 25 gig to 100 gig to 400 gig very quickly. Security and that ability to deploy different types of security has become critical. And then again, flexibility to future-proof things because you can't afford to redeploy these architectures. For us, that means that our innovations at Achronix are first of all on the data acceleration to make sure that we can seamlessly deploy between the cloud and the edge. Secondly, to look at, from a memory standpoint, on-chip, on-package, and in-board to make sure that the performance of the memory system is optimal. We look at SerDes technology for maximizing that data network connectivity. We look at configuration in terms of security, both for data in motion and data in rest, as well as sophisticated security to be able to configure and program these devices. And then finally, we're obviously making sure that we have very flexible engines, because as I said, what you're seeing is a migration from high precision floating point arithmetic all the way down to small precision fixed point arithmetic. So you need that flexibility. So we see that we're about to go into a very, very new era, which is exciting for all of us in terms of opportunities, which is going to change our lives more than the PC era did, and more than the internet era did, and the advent of smartphones. I think that it's going to give us an opportunity to collaborate and work together as we have to build silicon systems, software systems, and deploy that infrastructure on a worldwide basis. And with that, thank you very much.
Thank you, Robert. Well, thank you for the kind words in the beginning for CASPA. I think for that, we would love to invite you back here again. By the way, did you come up with those three names? Speedster, Speed Chip, Speed Core.
We've got a very creative marketing team, and they came up with those names.
Wonderful. So for those of you looking for additional FPGA options, here we are. So at this time, we'd like to have Brendan to present a token of appreciation to Robert Blake.